sure you had different variations of concept maps, but it should look something like this. All right, you have a stimulus, which is detected by a sensor that is communicated to an integrating center. The integrated center then communicates an output signal to an effector, and that brings about a response. Now, when we have that response, that is going to turn off or negate our initial stimulus here. All right, so this is the component here that makes this a loop. This is going to go back and turn off the initial stimulus, and that creates a loop of events. Okay?
I drew so much shivering because it was pulled out and then all the.
Oh, that's a good example, actually. Yeah. Something similar. All right, so the mechanisms of negative feedback loops is that moves in the opposite direction from the change. So if something is decreased, we want to work to increase it. If something was increased, we want to work to decrease it. So that's the whole idea behind this feedback of events, is to turn off that initial stimulus. Right? Now that it makes change or deviation from the set point smaller. So making change or making deviation from the set point smaller is also turning off what? What is that turning off? If I'm decreasing the deviation from the set point, what am I decreasing or what am I turning off? Our error signal, right? So we're going to decrease or turn off the error signal. And it reverses the change in the set point. It's going to essentially bring things right back to where they want to be. Now, this is a continuous process, right? We're never fully in homeostasis, and that's it, the end. Right? Homeostasis is an idea of continually striving towards this state of balance. So you're always making fine-tuned adjustments. You're always detecting any additional changes, and you're continually monitoring your pH, your blood pressure, your temperature, your glucose, and so on and so forth. Right? So you're not in homeostasis and that's it, but it's a state that we're continually striving towards. All right, so similar to what, remind me of your name? Thomas just said, is an example using the body temperature. All right, so sensors in the brain detect a deviation from 37 degrees Celsius. Okay? Another part of the brain is going to assess that this is off. So it's going to send a signal to your effector. Oops. Send a signal to your effector, which is your sweat glands, and that is going to stimulate the body to cool down itself in the form of sweat. Once the body is now cool enough, right, we're going to inhibit that sweat gland signal. That's turning off the initial stimulus. And the end result is that we're going to regulate this process continually. So we're going to continually detect any new changes in temperature. And this is why it's called a loop. It's a continuous process, right? In the case where we get too hot, or in the case when we get too cold, we're going to shiver. And that is going to help bring the temperature back to 7. Now, homeostasis is often maintained using opposing factors, right? So again, sweat glands versus shivering, right? Sweating versus shivering. So we're moving in opposite directions to help to maintain this normal range, what we call dynamic constancy, right? The state of balance. So if something goes up, we bring it down, and so on and so forth. And we'll talk about a few examples of that. Now, there's also the concept of positive feedback. And positive feedback is the opposite of our negative feedback. This is where the process is continually stimulated. So you're going to amplify the signal or continue stimulating that loop. A good example is a damage to a blood vessel. If you damage or rupture or tear one of your blood vessels, the process of forming a clot begins. Now, clotting factors are going to start depositing at the site of that injury, and we're going to continue this. We're going to amplify. We're going to add more. This is a positive feedback signal until we have successfully repaired that injury or that damage. And once we do that, we would then send a negative feedback to stop the deposition of clotting factors. questions in that. Right, so this is an example of positive feedback. Right, so the process of forming the clock involves positive feedback, but to turn that entire thing off, we still need a negative feedback signal. So in that way, positive feedback can contribute or help to negative feedback. Question, Ryan?
So could it be said like from the integration center, what could a positive feedback start there?
Yep.
To the whole loop?
Yep, you can start a positive feedback. It just depends on what type of signal we're sending to the receptor. Is it more of this or less of this? All right, we're gonna look at a positive feedback example right now. All right, so the pituitary gland is one of the master hormone glands in the base of the brain, and it secretes a hormone called LH, or luteinizing hormone. And this is responsible for the ovulation that a woman goes through during her menstrual cycle. So LH is going to stimulate the ovaries, right, by sending an output signal. And that is going to help the ovaries to secrete estrogen. Now, the production of estrogen is going to potentiate more LH. So estrogen positively feedbacks to the pituitary gland and influences the secretion of more LH hormone. And so this is a continuous positive feedback cycle in that LH potentiates estrogen, estrogen potentiates more LH, and LH potentiates estrogen, on and on and on. Okay? Now after the LH surge, right, because now we have LH at a very high point after the LH surge, and we have ovulation, the ovaries stop secreting estrogen, and that is the negative feedback in that. That's going to turn off that signal until the next monthly cycle.